Optimization theory for AI from gradients to practical training. Taylor expansion. Real-world analogy. Use a magnifying glass on a curved surface. Up close, a curve becomes a line. Then a parabola once curvature joins the scene. The first order term is the local slope. The second order term adds curvature. In many dimensions, the gradient points uphill, and the Hessian describes how the slope bends. The derivation is a controlled zoom in. Match the value, then the slope, then the bend. That is why the pieces appear in this order instead of randomly. The gradient term tells which tiny move changes the loss fastest. The Hessian term warns whether that advice will remain true a moment later. In the story, Taylor expansion is the scout who reads the terrain before the hero takes a step. The optimization problem. Real-world analogy. Tune a radio dial until the static drops. The parameters are the dial positions, and the loss is the unwanted noise. Choose parameters theta so the loss f of theta is as small as possible. In linear regression, W and B move until predictions match the data. Real neural loss landscapes are usually non-convex. Optimization became the language of learning because training needs one target number to improve. The loss compresses many mistakes into a single battlefield. Convex problems are training wheels. The bowl has one bottom. Neural networks are the real dungeon, with saddles, flat corridors, symmetries, and many valleys that can still be useful. Hyperparameter optimization. Real-world analogy. Tune a race car before the run. Tire pressure, suspension, and gears matter differently, and testing every combination would take too long. Grid search multiplies every option, so it gets expensive quickly. Random search samples important dimensions better. Bayesian optimization uses expected improvement, and hyperband avoids wasting full training runs on weak settings. Hyperparameters are not learned by backprop, but they decide whether backprop has a fair fight. Grid search came first because it is obvious and reproducible. Random search became important when researchers noticed most knobs barely matter. Bayesian methods add memory and uncertainty, while hyperband adds ruthlessness. Weak racers leave the track early. Optimization tricks. Real-world analogy. A workshop saves memory, averages steady hands, and uses a mentor to slow reckless jumps when training gets unstable. Gradient checkpointing trades extra compute for memory. Stochastic weight averaging smooths the final solution. Look ahead lets a fast optimizer explore while slow weights move more steadily. These techniques exist because real training is constrained by hardware and noise, not just calculus. Checkpointing was born from the need to train deeper models than memory allowed. Weight averaging turns jitter into a smoother final model. Look ahead makes the optimizer feel less impulsive, like a mentor catching the hero before a reckless leap. Constrained optimization. Real-world analogy. A runner can sprint, but must stay inside the marked track. Projection and constraints keep every move legal. Projected gradient descent takes a normal gradient step, then moves the result back into the valid set. Lagrangian methods add a penalty term so the optimizer balances low loss with constraint satisfaction. Constrained optimization answers a real-world truth. Some answers are illegal no matter how low the loss looks. Projection came from geometry. Step freely, then snap back to the feasible set. Lagrangians came from economics and mechanics. Attach a price to violating the rule. The hero learns that power without boundaries is not mastery. Stochastic gradient descent. Real-world analogy. Estimate the mountain slope from the patch under your boots instead of surveying the entire mountain before every step. Full batch gradients inspect every sample. Stochastic gradient descent estimates the slope from a batch. The update is simple, but the noise acts like useful regularization. Stochastic gradient descent became dominant because full gradients are too expensive for huge datasets. It trades precision for momentum through time. Many cheap guesses beat one perfect measurement that arrives too late. The mountain analogy matters because the hero never sees the whole landscape, only enough ground to choose the next step. Optimization for sparsity. Real-world analogy. Prune weak branches from a tree so the strong roots get more light, memory, and attention. L1 regularization uses soft thresholding, which shrinks values and snaps small ones to zero. Magnitude pruning keeps the largest weights and removes the rest. Sparsity is not just smaller numbers, it is structure. L1 regularization became useful because its sharp corner at 0 makes exact deletion mathematically natural. Magnitude pruning is the battlefield version. After training, remove the weakest connections and see which pathways were truly carrying the story. Loss functions. Real-world analogy. Use scoring systems like archery. Measure distance from the bullseye for regression or target zone confidence for classification. MSE fits numbers. Cross-entropy trains classifiers. Label smoothing improves calibration. Multi-step latent losses train future representations. And anti-collapse terms keep embeddings informative. Loss functions are the laws of the world. MSE says big misses are dramatically worse. Cross-entropy came from maximum likelihood. The best classifier should assign high probability to what actually happened. Latent prediction, smoothing, and anti-collapse terms exist because modern models can exploit weak objectives unless the scoring system demands useful structure. Activation functions. Real-world analogy. Use decision thresholds like a smoke detector. Below threshold it stays quiet. Above threshold it fires. Without activations, stacked linear layers stay linear. ReLU is fast. Sigmoid gates values. Softmax normalizes competing scores. Modern transformers often use GeLU-style smooth gating. Activation functions are the moment the model gains expressive power. ReLU became popular because it was cheap and kept gradients alive on the positive side. Sigmoid and tanh shaped early neural networks and still power gates. Softmax turns raw scores into a contest where probability mass must sum to 1. A forward pass. Real-world analogy. An assembly line, where each station transforms the product and hands a changed version to the next station. Each layer multiplies by weights, adds bias, applies an activation, and passes the result onward until the final probability is produced. The forward pass is an assembly line. Weights mix evidence, biases set thresholds, and activations decide what passes onward. It is worth memorizing because every backward gradient is just the reverse accounting of these forward choices. If the forward story is confused, the backward story cannot save it. Backpropagation. Real-world analogy. Trace a river back to its source to see how each upstream branch contributed to the final flow. The loss derivative flows back through each operation. Every parameter receives a blame signal showing how changing it would change the loss. Backpropagation is not magic. It is dynamic programming on derivatives. It became the standard because calculating every derivative separately would be impossibly wasteful. The hero now learns accountability. Every operation must explain how it changed the final loss. Learning from mistakes. Real-world analogy. Adjust a recipe after tasting. Too salty means reduce salt next time, and every ingredient gets some responsibility. After backpropagation, each weight is updated by subtracting learning rate times gradient. In the worked example, the prediction moves from 0.746 toward the target. This chapter is where theory becomes training. The derivation says, if the gradient is local slope, then subtracting it should reduce loss for a small enough step. The worked example matters because it closes the loop. Forward prediction, loss, gradient, update, then a better forward prediction. Adaptive learning rates. Real-world analogy. Smart cruise control slows on winding roads with unstable gradients and speeds up on straight highways with consistent signals. AdaGrad accumulates all squared gradients, which can slow too much. RMSprop uses an exponential average so old gradients fade. Adaptive learning rates were invented because one global step size is unfair when different parameters live on different scales. AdaGrad was brilliant for sparse features but could freeze after too much history. RMSprop added forgetting, making the optimizer responsive again. Gradient descent. Real-world analogy. A ball rolling downhill follows the steepest descent it can feel from where it currently sits. Gradient descent repeatedly subtracts a scaled gradient. Two smaller step crawls. Too large a step can diverge. Gradient descent is the hero's first sword. It follows from Taylor expansion. To lower the next value, choose a direction with a negative gradient dot product. It is not always the fastest method, but it is the grammar every later method speaks. Gradient problems. Real-world analogy. Cliffs, plateaus, and saddle ridges make the route dangerous, so the traveler needs survival tactics. Sigmoid chains can make early layer gradients nearly vanish. Exploding gradients are controlled by clipping. Saddle points need noise, momentum, or curvature information. Deep learning forced optimizers to survive hostile terrain. Sigmoid derivatives below 1 multiply into silence. Recurrent loops can multiply into explosions. Residual connections, normalization, clipping, and better activations are the survival gear that made deep models trainable. Dropout. Real-world analogy. Training a team with random members absent forces everyone to become versatile instead of depending on one star player. Dropout prevents a model from relying too heavily on one path. The scaling keeps training and inference magnitudes aligned. Dropout became famous because it made networks less dependent on fragile feature alliances. The team member analogy is exact. If a teammate may vanish, everyone learns broader skills. At inference, the full team returns. So scaling keeps the strength consistent. Mixed precision. Real-world analogy. Use rough calculations for speed but keep precise records where a tiny bookkeeping error would erase the signal. The key risk is underflow. Tiny gradients round to zero. Loss scaling enlarges them for backpropagation, then unscales before the optimizer step. Mixed precision is packed with the machine. GPUs can perform lower precision matrix multiplies very quickly, but optimization still needs trustworthy gradients. Loss scaling exists because a gradient rounded to zero is not a small mistake. It is a severed signal. Distributed optimization. Real-world analogy. Multiple teams explore different parts of a mountain, then share findings before choosing one shared route downward. Data parallel workers compute local gradients, average them, then step together. Gradient accumulation increases effective batch size without increasing memory per mini batch. Distributed optimization exists because modern models are too hungry for one device. The math is simple, but the system is not. Every worker must agree on the update. The story becomes a guild quest, where isolated discoveries only matter after they are shared. Normalization. Real-world analogy. Adjust test scores. Batch norm grades across the class, while layer norm normalizes one student's scores across subjects. Batch normalization uses batch statistics, which can depend on batch size. Layer normalization works per sample, making it well suited for transformers and variable sequence lengths. Normalization changed training because it made deep networks less sensitive to unlucky scales. Batch norm grades across the class. Layer norm grades one student's subjects. Transformers rely on layer norm because tokens and batch sizes vary, but each token still needs a stable residual stream. Convergence analysis. Real-world analogy. An ETA board with confidence bounds tells not just that you should arrive, but how quickly and under what assumptions. Linear convergence reduces error by a constant factor. Sublinear rates are slower. Newton-style methods can become quadratic near an optimum under the right conditions. Convergence analysis is the map legend. It explains why some quests end quickly and others crawl. The constants mu and L describe the terrain's kindness. A good practitioner remembers rates because they separate real bugs from mathematical reality. Momentum methods. Real-world analogy. A heavy ball remembers past pushes and rolls faster through consistent valleys while resisting sudden sideways wobble. Momentum accelerates consistent directions and damps zigzags. Nesterov momentum asks where velocity will take us before measuring the next gradient. Momentum came from physical intuition. A heavy ball should not forget every previous push. In narrow valleys, plane descent wastes energy bouncing between walls. Momentum turns repeated agreement into speed, while Nesterov adds foresight. Discretization and quantization. Real-world analogy. Convert analog audio into digital samples, then round values into fewer levels when storage and speed matter. Discretization samples dynamics at a step size. Quantization maps floating point values to fewer integer levels, saving memory and compute with controlled error. Discretization and quantization are how continuous math enters digital hardware. The sampling theorem explains why time steps cannot be arbitrary. Quantization exists because memory and bandwidth are often the real bottleneck. The hero learns that precision is a resource, not a religion. Optimization debugging. Real-world analogy. Inspect every station on a factory line instead of only staring at the broken final product. Gradient checking verifies backprop. Teacher-forced and recursive rollouts expose compounding error. Temporal straightening checks whether latent motion is consistent. Debugging is the detective arc. A model that fails to learn is not a mystery. It is a set of measurements waiting to be isolated. Gradient checks test calculus. Rollouts test deployment. Latent geometry tests whether the hidden world is navigable. Architecture-specific optimization. Real-world analogy. Race cars, cargo ships, and drones all need different tuning even though each uses engines, controls, and safety limits. Transformers need attention scaling, warm-up, and often a damn war lamb. RNNs need clipping. Learned control uses sampling weights and domain randomization for robustness. Architecture-specific optimization is the master-level arc. Transformers, convolutional nets, recurrent nets, and controllers all fail differently. Scaled attention came from variance control. LAM came from huge batches. MPPI came from control, where sampling can be easier than differentiating the whole decision process. ADAM. Real-world analogy. Combine momentum with adaptive brakes, so each coordinate moves with speed, memory, and caution. ADAM tracks the mean gradient and mean squared gradient, corrects their early bias, then normalizes each coordinate's update. ADAM became the default because it fuses two survival skills, momentum and adaptive step sizes. The bias correction is not decoration. Early moment estimates are too small because they begin at 0. ADAM lets the hero move quickly without trusting every coordinate equally. ADAM. Real-world analogy. Use consistent friction rather than brakes that behave differently at different speeds. With ADAM, weight decay is not distorted by the adaptive denominator. That makes regularization more consistent across parameters. ADAM exists because adaptive optimizers made old weight decay behave inconsistently. L2 regularization was historically equivalent to weight decay for plain SGD, but ADAM's denominator broke that equivalence. Decoupling restored the intended meaning. Discourage large weights without letting gradient variance rewrite the rule. Learning rate scheduling. Real-world analogy. Drive by warming up, cruising on familiar stretches, then slowing near the destination. Warm-up starts cautiously, especially for large models and batches. Cosine schedules then reduce the step smoothly as training approaches the destination. Learning rate schedules exist because the best step size changes during training. Early on, the model is fragile and ADAM's moments are immature. Later, larger moves explore. Near the end, smaller moves refine. The schedule is the pacing of the entire journey. Second-order methods. Real-world analogy. Use a topographic map instead of only a compass, because curvature changes what a wise step should be. Newton's method rescales the gradient by the inverse Hessian. It can converge quickly, but storing and inverting Hessians is expensive and curvature may point the wrong way. Second-order optimization asks for more intelligence per step. Newton's method came from approximating a function by a quadratic and jumping to that quadratic's minimum. It can feel like teleportation near the answer, but the cost of full curvature keeps it from ruling deep learning. Quasi-Newton methods. Real-world analogy. Navigate with a map that improves after every step and every new slope observation. BFGS updates a Hessian inverse estimate from observed steps and gradient changes. LBFGS keeps only recent pairs, reducing memory from quadratic to linear in parameter count. Quasi-Newton methods are cartographers. They do not demand the entire topographic map in advance. They update the map from footsteps. BFGS became beloved because it often captures useful curvature without exact Hessians. LBFGS made that idea practical at larger scale. Natural gradient descent. Real-world analogy. Navigate on the curved Earth rather than a flat paper map, so distance means the right thing. Standard gradients measure distance in parameter space. Natural gradients measure change in probability distributions, using the Fisher information matrix. Natural gradient asks a deeper question. Should two parameter moves count as equal if one barely changes the model's predictions and the other changes everything? Information geometry says no. The Fisher matrix makes the update respect the model's output distribution. Trust region methods. Real-world analogy. A GPS confidence radius. Trust directions nearby, but recalculate when the proposed step reaches beyond reliable territory. A trust region solves for the best step inside a radius, then compares actual improvement with predicted improvement before accepting and resizing the region. Trust region methods are cautious strategists. Taylor expansion is powerful nearby and dangerous far away. The trust radius encodes humility. If the local prophecy was wrong, shrink the circle. If it was right, let the hero stride farther. Line search. Real-world analogy. You know which direction to walk, but still need to choose the distance that improves the journey. Backtracking line search starts with a full step and shrinks it until the loss decreases large enough. Line search exists because knowing the direction is not the same as knowing the stride. Armijo asks for sufficient reward before accepting a step. Wolf conditions add a curvature check, making sure the step length matches the slope's change. Coordinate descent. Real-world analogy. Tune equalizer knobs one at a time. listening after each change before moving to the next control. It is useful when subproblems are cheap or have closed forms, as in lasso and matrix factorization. Coordinate descent came from the oldest practical instinct. When the full problem is hard, fix everything else and solve one piece exactly. It is not flashy, but for sparse regression, matrix factorization, and separable structures, it can be devastatingly effective. Proximal methods. Real-world analogy. Step freely, then project or correct back into the valid region when a sharp rule or constraint is waiting. First take a gradient step on the smooth part, then the proximal operator handles sparsity, constraints, or other non-smooth penalties. Proximal methods are the peace treaty between gradients and non-smooth rules. A plain gradient cannot handle a sharp absolute value cleanly, so as to split the problem. Gradient for the smooth loss, prox for the sharp penalty. Pfister adds momentum and turns patience into speed. Key takeaway. Start simple, monitor gradients, tune deliberately, and match the optimizer to the architecture.